Then let us begin our today's session. Mostly I will conclude the concept of improper integrals today. I will give the total view of the chapter. And for some problems, I will give the posters in Telegram. You can check for that because it is very easy, just calculating the integration. So let us begin with the problem. Integral 2 to 3 dx by x minus 2 whole power 1 by 4 into 3 minus x whole square. Please consider this problem. So as per the previous discussion, the interval is finite, and what are the points of discontinuity here? The infinite discontinuity from the given function on observation. 2 and 3, because here if you substitute 2, you will get the point of discontinuity, and here 3 is the point of discontinuity. So while evaluating the integral, you are going to consider it as integral 2 to 3. The given part is equal to integral 2 to a dx by x minus 2 whole power 1 by 4 into 3 minus x whole square plus integral a to 3 dx by x minus 2 whole power 1 by 4 into 3 minus x whole square. So earlier we have considered only one point of discontinuity. Here we are considering the both points as the discontinuity. So at this portion you are going to split that. So in order to verify the convergence of the given integral, since it is equivalent to sum of the two values, you should be able to prove that the first integral is convergent as well as the second integral is convergent. If both are convergent, then only this value is convergent. If one of them is divergent, the result is nothing but divergent. Okay? Is it clear? Right. Now, let us consider the first one. Since here 2 is the point of discontinuity, so we are using the comparison test for the evaluation of the integral. It means for the convergence of the integral. So at this portion, you take g of x is equal to 1 by x minus 2 whole power 1 by 4. So if you apply the limit extends to 2 plus f of x by g of x, then it is equivalent to limit extends to 2 plus the value will be 1 by 3 minus x whole square, and it is nothing but 1. Since it is non-zero and finite, the integral f and integral g both converge or diverge together. So by limit comparison test, integral 2 to a f of x dx and integral 2 to a g of x dx both converge or diverge together. So if you consider integral 2 to a g of x dx, so from the comparison integral, is it convergent or divergent? Can you say? Convergent, because as and when you consider the form integral 1 by x minus a whole power n, as and when n is less than 1, it is convergent. Since 1 by 4, which is less than 1, integral 2 to a g of x is convergent, hence the first integral is convergent. That is the discussion about the first integral. Is it clear? Now, let us go with the second integration. Can I erase this? Fine. So if you consider the second integral, since in the two functions, this is giving the discontinuity, let us take that g of x is equal to 1 by 3 minus x whole square. where 3 is the point of infinite discontinuity. Yes, second one is divergent. So if you consider limit x tends to 3 minus f of x by g of x, it is equivalent to limit x tends to 3 minus 1 by x minus 2 whole power 1 by 4, which is a finite number. It is nothing but 1, which is non-zero and finite. So by limit comparison test, both the integrals either converge or diverge together. Since integral a to 3 g of x dx is equal to integral a to 3 1 by 3 minus x whole square dx is divergent because the power is greater than 1 here. So hence from the comparison integral, it is divergent. Therefore, by limit comparison test, it is divergent. So the total result is the given integral is divergent. Okay. So please take a note of it. Then I will go with the other ones. Once you have noted, please inform me. Right. Now let us consider the problem integral 0 to 2 log x by root of 2 minus x dx. Please take a note of it. Let us discuss over this. Now, if you observe the problem, here 0 is a point of discontinuity and 2 is also a point of discontinuity. Accepted? So how we are going to split it? It is equivalent to integral 0 to 1 log x by root of 2 minus x dx plus integral 1 to 2 log x by root of 2 minus x dx. Now please understand one thing, that as and when we are applying the comparison test, we should be authentically say that what is the value of g. So while writing g, if you are writing the power of x, you should mention what is the power of x there particularly. Now if you consider the first integral, let us evaluate the convergence one after the other. So here from 0 to 1 log x value is negative. As and when we start the procedure, it is mandatory that the given function must be positive. It should take positive values for the interval on which you are checking the convergence. As and when it is taking the negative values, we should take minus f of x and we should do the procedure for the minus f of x. So we consider minus f of x is equal to minus log x by root of 2 minus x, because log x is negative over the interval 0, 1. Is it clear? Right. Now we are going to verify the convergence of this. Now how to take g of x? First of all, let us take that. Take g of x is equal to 1 by x power n. Actually, I should mention what is the power of n. So for this type of problems, always we take g of x is equal to 1 by x power n, and at the end, while defining the convergence, we will mention what is the value of n. Okay. So please take a note of it. Since 0 is the point of discontinuity here, let us apply the limit. So limit x tends to 0 plus f of x by g of x, if you consider, this is equal to limit x tends to 0 plus minus log x into x power n by root of 2 minus x. As we know, we have a formula for all n greater than 0. Limit x tends to 0, x power n log x equal to 0. So this value is equal to 0. Is it clear for you? I have mentioned the formula earlier. Limit x tends to 0 plus x power n log x equal to 0. Now what happens? We should mention what is the power of n here. What is the value of n here in g of x? So by limit comparison test, both the integrals either converge or diverge together. So in other words, as and when the limit is 0, if denominator is convergent, then numerator is convergent. That is, if integral g of x is convergent, then only integral f of x is convergent as per the comparison test is concerned. So if you want to say that integral 0 to 1 x power n dx is convergent, so what must be n? Always we should have n must be less than 1. So you can set any value for n between 0 and 1. So take n is any value between 0 and 1. Why? Because for all n greater than 0, the limit equals to 0 here. So you can take any positive value for n. So in order to get a convergence of the integral, you should say that n must be less than 1. So that's why I am taking that. Yes, there is another form of limit comparison test too. That is what I am mentioning. As and when the limit is existed which is not equal to 0 and finite, both converge or diverge together. Right. As and when the limit is 0, depending upon the convergence of g, f will be convergent. The same thing you have done in limit comparison test of infinite series too. You can check for the condition. The same condition we are applying here. That's it. No change at all. So as and when denominator is convergent, then numerator is convergent. So we should find a function g which is convergent. That's why I am setting n as any value from 0 to 1, in between 0 and 1. Therefore, integral 0 to 1 g of x dx is convergent, hence f of x is also convergent. Okay. So here we are verifying the convergence for minus f of x. Please understand, because f is taking negative values on the given interval. Okay. Is it clear for everyone? The procedure for the first integral. Shall I continue? That's why what I am saying, if you are observing a comparison integral, you should find a function g, that's all. Any function you should be able to find. Please understand, the whole concept of comparison integral is nothing but whenever you have f of x, you should find a g of x such that f of x by g of x must have a limit. Here g of x is arbitrary. Any kind of g of x you can take. That's why I am defining g of x by default as 1 by x power n, and I am setting a value for n. This could be taken as n, so that I am going to get the value. Comparison test is applicable, that's all. Obviously, if you take n is equal to 2, comparison test fails here. Always you will get divergence. The thing is, at least you should find one function. That's all for the comparison integral. Is the concept clear for everyone? So always we take g of x is equal to 1 by x power n, and based on that we will fix a power of n, what it could be. That's all. So the first integral is convergent. Coming for the second integral, we do the regular procedure. So for the second integral, here log x takes the positive values. It also takes the positive values. 2 is the point of infinite discontinuity here. Now what happens? Let us take g of x is equal to 1 by root of 2 minus x. Now if you consider limit x tends to 2 minus f of x by g of x, it is equal to limit x tends to 2 minus log x, and its value is nothing but log 2, which is a finite value. Therefore, by limit comparison test, both the integrals converge or diverge together. Since integral 1 to 2 g of x dx is equal to integral 1 to 2 1 by 2 minus x whole power 1 by 2 dx is convergent. The comparison integral is convergent since the power is less than 1. Therefore, this integral is also convergent. Since both integrals are convergent, this is the convergent integral. Okay. Is the concept clear to all? So please take a note of it. Then I am going to take a similar kind of problem here. Then you will get the idea. So the other problem I wish to take is, take integral 0 to 1 log x by root x dx. Let us take this problem. Now, what is the point of infinite discontinuity here as per the interval considered? Say 0. Right. Since the function log x takes negative values, we should consider the function minus f of x. So in the previous case also, we have taken minus f of x and calculated limit extends to minus f of x by g of x. Please understand that. That we did actually. Now there is no need to split the interval because it has only one point of infinite discontinuity. One is not at all a point of infinite discontinuity. And how should we take g of x here? Now by default, you take g of x is equal to 1 by x power n. Now at the end, after doing simplification, we should mention what could be the possibility of n. That is the whole idea behind this. So for every problem, we take 1 by x power n. And at the end, we specify the value for n, right? So if you consider limit extends to 0 plus minus f of x by g of x, the part, this is equal to limit extends to 0 plus, so minus x power n log x by root x. That you can write. And since x is there, you can further simplify this as accepted all. Say right. Now what happens? If you apply limit, the limit will be 0 as and when the power is positive. Because the formula is given that limit extends to 0 plus x power n log x equal to 0 for all n greater than 0. So here we need to understand that whatever the power n you write here for x, it must be positive. So if you want to say that the limit is 0, it must be positive, greater than 0. So from this we say that n is greater than 1 by 2. Accepted? All. Any questions? Now here what happens, if you want to set a function g which is convergent, the power must be less than 1. That is the condition. And if you want to say that the limit is 0, that is limit existed, the power must be greater than 1 by 2. So comparing these two, we should fix n, the power, as a number between 1 by 2 and 1. So choose n between 1 by 2 and 1. Therefore, what happens? Integral 0 to 1 g of x dx is convergent. Therefore, by limit comparison test, given integral is convergent. That is the conclusion. Okay. So for every problem, we take g of x is equal to 1 by x power n, and after the limit evaluation, we should fix a value for n. This is the possibility for n to get the convergence. If n takes this type of value, we should get divergence. Okay. I think this will give the clear idea or the procedure, how we are specifying a number for n. Any more doubts to anyone? So let me take the other problem. So the next problem I wish to take is integral 0 to 1 log x by 1 minus x square dx. Please take a note of it. Now, if you observe that, what are the points of infinite discontinuity here? Please tell for this problem. Right. Actually, if you observe that since log 0 is undefined, it is a point of infinite discontinuity. And if you substitute 1 in denominator, you will get a point of infinite discontinuity. But actually, let us check the part that what happens for limit x tends to 1 minus log x by 1 minus x square. Since it is in the undefined form, while applying the limits, so let us apply L'Hospital rule. So since the interval is taking negative values, you should take the function as negative minus f of x. So you take minus. So this is equal to limit x tends to 1 minus 1 by x by minus 2x, and this is equal to 1 by 2. Accepted? So the thing what I want to emphasize here is, if you observe that the point is an infinite discontinuity point, please ensure that by checking the limit. If limit is existed, we cannot treat the point as the point of infinite discontinuity. So even though 0 and 1 are observed to be point of infinite discontinuity, we should take 0 only as the point of infinite discontinuity. 1 is omitted because the limit value is existed here. Okay. So we mentioned that by calculating limit and showing that the limit is 1 by 2, 0 is the only point of infinite discontinuity that we should mention. Clear? If both the points are infinite discontinuity, we should split it. The integral must be split into two parts and we should verify individually. But here the case is different. Is it clear to all what I mentioned? Any questions? Fine. Now, 0 is the only point of infinite discontinuity, and let us do the same procedure as it is. So you take g of x is equal to 1 by x power n, right? And you consider limit x tends to 0 minus f of 0 plus minus f of x by g of x. This is equal to limit x tends to 0 plus minus log x into x power n by 1 minus x square. So the limit part will be 0 if n is greater than 0. So I am applying the same limit condition. So if you put n as any number between 0 and 1, then what happens? The comparison integral 0 to 1 g of x dx is convergent. Hence, by limit comparison test, the given integral is also convergent. That was the conclusion. So please check on that. So you take the problem as integral 0 to 1 x power n log x whole divided by 1 plus x whole square dx. You take the problem like this. Now let us discuss how to solve this problem. Now what happens? In the numerator, x power n is present. So n must be any number. N must be 0, n is positive, or n is negative. So we are going to verify the convergence in all the possible cases. So let us take that n equal to 0. Then what happens? The function is going to be log x by 1 plus x whole square. Since on the interval log x takes negative values, we should apply the comparison for minus of f of x. So we should consider the function minus log x by 1 plus x whole square. Now as usual, you take g of x is equal to 1 by x power n. So if you observe limit x tends to 0 plus minus f of x by g of x, it is equal to limit x tends to 0 plus minus x power n log x by 1 plus x whole square. And this value is 0 when n is greater than 0. Because when n is greater than 0, this numerator gives 0 value to us. So if you set n as a number between 0 and 1, the comparison integral is convergent. Hence, by limit comparison test, given integral is also convergent. Okay, so please take a note of that. After noting, you please inform. Right? Now let us take the case that n is negative. Suppose n is negative. Now what happens? You can write n as n is equal to minus m, where m is positive. Every negative integer, every negative number can be written like this. So as usual, if you consider minus f of x, so it will be written as the given function f of x can be taken as log x by x power m into 1 plus x whole square. I am taking minus f of x. Accepted all? Right. Now as usual, we should define the comparison integral, and in the power, what could be the possibility of n? If you are able to specify that this is the possibility of n, automatically you have verified the convergence. So you should take g of x is equal to 1 by x power q. Why I have taken 1 by x power q? Already n and m, both numbers are used. So for a change, you take g of x is equal to 1 by x power q. So if you observe the limit x tends to 0 plus minus f of x by g of x. So this is equal to limit extends to 0 plus minus. So if you take the values in the numerator, x power q minus m into log x by 1 plus x whole square. Please check on that. Accepted? And we know that the limit value is 0 if the power is positive. That means if q minus m is greater than 0, then only the limit will be 0. In other words, q must be greater than m. This is one observation we got here. And the other one is, we always know that if you are using a comparison integral for the finite interval, the power here must be always less than 1. So we must have q less than 1. So in order to specify the comparison integral 1 by x power q, we should know what is the possibility of q here. So for q, we got two conditions. One condition is 0 less than q less than 1. Another condition is q greater than m. So what could be our possibility? 0 less than, m less than, q less than 1. So from this, what we can say about n? Because n is equal to minus m. So from this we say that m is less than 1. So minus m is greater than minus 1. So n must be greater than minus 1. So if you have say that the given integral is convergent, n must be greater than minus 1. Because here you have x power n is there. So since you have specified n greater than minus 1, whatever the number you take greater than minus 1, always we get the convergence. So there is no need to verify separately that what happens if n greater than 0. That case trivially comes at this position. Right. This is the solution of the problem. Please check on that. Is the part clear for everyone? How we have specified that? Yeah. I am saying that we are verifying the case of n less than 0, isn't it? Right. So for what values of n the given integral is convergent? That we actually verifying. Now what happens? For the convergence, we should know the comparison integral. What is the possibility of g? We must be able to specify. So after doing this part, we observed that qv is lying between 0 and 1 and qv is greater than m. So what happens? This is the inequality we observed, 0 less than, m less than, q less than 1, and from this m less than 1 we observed. Accepted? Or any more doubts? You are verifying the case n less than 0 means for what negative values the given integral will be convergent. In other words, from what negative values onwards in place of n, you will get the integral to be convergent. That is the whole idea. Please understand, since n is less than 0, you have written n as minus m. So from this part, you observe that n is greater than minus 1. So in place of n, you can take any number which is bigger than minus 1, so that by comparison integral and limit comparison test, the given problem becomes convergent. Okay? Clear? So if you summarize the previous part and this part, Earlier you have proved that at n is equal to 0, it is convergent. In this case, you have proved that from -1 onwards, whatever the value of n you have taken, it is convergent. It means that if you take n is equal to -1 or before this, it will be divergent. If you take any number bigger than -1, it is convergent. So here this is the possibility that n must be positive. This case already comes into this portion. That what I mentioned. Okay. So actually, if you want to verify the convergence, we should take three cases: n equal to 0, n is greater than 0, n is less than 0. So we have done with n equal to 0. We didn't choose n greater than 0. We have started with n less than 0. In this part, automatically this part came. Because from n greater than -1 onwards, everything is convergent. Fine. Is it clear to all? Yeah. Now let me take one more problem. It is also just like the comparison integral part. Later I will move with the other concepts. Please understand that whatever the case you choose, for each case we should mention what is G. Okay. So if you take the case n equal to 0, the given function is nothing but log x by 1 plus x whole square. So for this function, we are verifying the convergence, and in this, what G you are using? So there, I have used G as 1 by x power n, where n is any number which is lying between 0 to 1. Okay. Right. Now, I skipped this case. I have started with the case n less than 0. Then the given function is nothing but x power n into log x by 1 plus x whole square. Here also I want to know what type of G I must use for comparison integral. So there what happened, I have defined G as 1 by x power q, and I specified that q must be greater than m and n is equal to minus m. So obviously I get that n is greater than -1. So from n greater than -1 onwards, if you choose q as greater than m, then the given integral is convergent. That was the idea. Right. So if you have little confusion, if n is equal to -1.5, since right, n is equal to minus m you have taken, so m is equal to 1.5, you should take q is greater than 1.5. If you take q is equal to 1.6, then the comparison integral is existed, given integral is convergent. That was the idea. Okay. I think this gives the clarity for everyone. Let us do one more similar problem, then you have a full clarity. So this is the problem. Integral 0 to pi by 2 sin x by x power p dx. Let us take this one. So since the function assumes positive values here, so here f of x is equal to sin x by x power p, and you take the comparison integral, g of x is equal to 1 by x power mu. We should mention what could be the possibility of mu here. Okay. So if you consider the limit limit x tends to 0 plus f of x by g of x. It is nothing but limit x tends to 0 plus x power so mu minus p into sin x. So for the limit evaluation, I want to multiply and divide with x. So it will be limit x tends to 0 plus x power mu minus p plus 1 into sin x by x. And you are going to evaluate the limit here. Okay. Now, if you calculate the limit, you are getting different possibilities. Since it is a product, so you are applying the limit for this part and this part separately. This part limit is 1, we know that. So, if limit x tends to 0 plus, what is the value of this one? X power mu minus p plus 1. So here you have different answers. Depending upon the power you have considered, if the power is 0, it is nothing but x power 0, so the limit value is 1. Accepted? If mu minus p plus 1 is a positive number, so x power positive number, so limit x tends to 0, x power something, if you consider, it is 0. If the power is negative, then 1 by x power something you will get. Limit x tends to 0, 1 by x power something is nothing but infinity. Accepted? So, what is the thing you got? If mu minus p plus 1 equal to 0, the limit value is 1. Mu minus p plus 1 is positive, the limit equal to 0. Mu minus p plus 1 is negative, the limit equal to infinity. Accepted all? Right. So, you are taking each case, and each case you should mention what could be the possibility of p as well as possibility of mu, because you should have a comparison integral, right? So for comparison integral, always we will have 0 less than mu less than 1, then only the comparison integral is convergent. So if you take the first case, mu is equal to p minus 1, right? So you have 0 less than p minus 1 is less than 1. So from this, 1 less than p less than 2. Accepted? So if mu is equal to p minus 1, then 1 less than p less than 2 must be there, then it will be convergent. Accepted all? Are you getting the idea or not? Yes or no? Right. So if you take the second case, mu minus p plus 1 greater than 0, that is mu is greater than p minus 1. The second case. Always we know that for the comparison integral 0 less than mu less than 1, it is nothing but 1 is greater than mu is greater than 0. We know that mu is greater than p minus 1. So 1 is greater than mu is greater than p minus 1, which is greater than 0. So 1 is greater than p minus 1 is greater than 0. So from this we say that 2 is greater than p is greater than 1. Am I correct? Similarly, we take the third case too. So in each case, we will mention mu, what is the possibility and what is the possibility for p. That is the whole thing we are doing here. Okay. So in this way, we will evaluate the problem when undefined power is there. Let me take one problem which is given in the previous year problems. So you consider the integral 0 to pi by 4 1 by root of tan x dx. I think it is given in the previous year papers. So please take a note of it. Now, what is the point of discontinuity here? 0 and pi by 4 in the two things, 0. So, the function f of x is given as 1 by root of tan x, and for limit evaluation, I want to simplify this as it is nothing but 1 by root of sin x by cos x. So, this is equal to root of cos x by root of sin x. Accepted? Right. And we should have a comparison integral always. So here, let us take g of x is equal to 1 by root x. Why straight away I am taking it as 1 by root x? Always we take g of x is equal to 1 by x power n, and n must be less than 1 to get the convergence. Here square root is presented, that's why I have taken g of x is equal to 1 by root x. So if you apply, or if you consider limit extends to 0 plus f of x by g of x, then it will be limit extends to 0 plus root x by root sin x into root cos x accepted. And its value is nothing but 1, the limit value. Since limit is existed and it is a finite value, both integrals either converge or diverge together. Since this is convergent because the power is less than 1, by limit comparison test, given integral is also convergent. So please take a note of that. Then we are entering into the final stage of the problems. Of improper integrals. So far, from the previous two sessions, we have discussed about the convergence of integral a to infinity, integral minus infinity to infinity, and integral minus infinity to some number b. And later, we have discussed the case of integral a to b, where a is a point of discontinuity, sometimes b is a point of discontinuity, sometimes both a and b are point of discontinuity. This is the thing you have done totally. Now what happens if you take integral a to infinity, and if you take a finite interval, what is the other technique to verify the convergence? So here we use the concept of absolute convergence. Suppose we have taken a finite interval integral a to b. We say that the given integral is absolutely convergent if integral a to b mod f of x dx is convergent. Fine. So this convergence automatically implies the regular convergence. So if you are able to prove that this is convergent, automatically this will be convergent. There is no need to separately consider this function. Okay. For finite interval, you will take that type of logic also. For this, I just want to take one problem, then we'll go with the others. Shall I take? One problem is enough to get the idea. Suppose you take the convergence for integral 0 to 1 sine 1 by x by root x dx. So you actually observe that 0 is the point of infinite discontinuity, how to define g, etc., etc. These are some interesting concepts before us. Now what happens here? F of x is equal to sine 1 by x by root x. So apart from verifying convergence for f of x, we verify the convergence for mod f of x. So if you consider mod f of x, this is equal to modulus of sine 1 by x by root x. Applying modulus individually, which is less than or equal to 1 by root x. Accepted? Yes or no? Because modulus of sine theta is less than or equal to 1. So please understand, you have a series like this, un less than or equal to vn. Now what happens if the bigger series is convergent? This series is convergent. So integral 0 to 1 mod f of x dx is less than or equal to integral 0 to 1 1 by root x dx. From this observation, since it is convergent, we know that because the power is less than 1 by 2, this is also convergent. So the integral converges absolutely. Since absolute convergence gives regular convergence, this is convergent. So we write that integral 0 to 1 mod f of x dx is convergent, hence integral 0 to 1 f of x dx is convergent. That is the conclusion we write at the end. So what we are doing? We are considering mod f of x. We got a comparison integral. Since the upper integral is convergent, which is giving a finite value, the lower integral is also convergent. Since it is contains modulus, the modulus of f of x is convergent. So f is also convergent. Okay. Please confirm our reply. Now, so far we discussed a finite interval convergence in which the function has a point of discontinuity. Now, what happens? We are entering into the third kind, the last model of the improper integrals. Suppose you have taken an infinite interval and sometimes you have the point of discontinuity too. The third kind we are discussing. And one interesting thing is the concept of comparison integrals we also use when the interval is infinite. In other words, I am going to say, if we have taken a finite interval integral a to b f of x, you are defining some g. Based on g, you are saying f is convergent or not. Similarly, if you take an infinite interval, say a to infinity, this type of model we consider. Integral a to infinity we consider. So if you want to say this is convergent, here also we set up a convergence integral. So we check for integral a to infinity of g, right? So not only for finite interval, for infinite interval also we define a comparison function g. Okay. So it is very simple. As we know that for the finite case, we are going to verify 1 by x minus a whole power n dx is convergent if n is less than 1. So whenever you take a finite interval, if you are verifying the comparison integral, if the power is less than 1, it is convergent. For the infinite case, the power must be greater than 1. So if you take integral a to infinity 1 by x power n, if the power n is greater than 1, then this integral is convergent. So please take a note of that. So integral a to infinity 1 by x power n dx is convergent if n is greater than 1 and a is a positive number. Integral a to infinity 1 by x power n dx is convergent if n is greater than 1, where a is a positive number. So this is the useful comparison integral we will do while taking the problems. So if I take 1 or 2 problems, you will get the idea automatically what it is actually. So can I take the problem? So the first problem I wish to take is integral 1 to infinity x cube by 1 plus x power 1 plus x whole power 5 dx. So let us take this one. Now here what happens, if you have a function f, I am going to set up a comparison integral here, right? So if you take x as common here, accepted, say. So after taking common, whatever the part remained, you take it as g. So you take that g of x is equal to 1 by x square. So please understand, in the finite case, if a is the point of discontinuity, you are calculating limit extends to a plus f of x by g of x, right? Since you have taken the infinite interval, the limit case will be modified as limit extends to infinity f of x by g of x. So here also we are using the limit comparison test. The only difference is, in the earlier case you are checking for limit extends to a, here you are checking for limit extends to infinity. That is the only difference. There you take a function g where the power n is less than 1. Here you take a function g where the power n is greater than 1. That is the only difference. Okay. So if you want a strategic idea, you have a finite interval, you have infinite interval. So for the finite case, we will check for limit extends to a f of x by g of x, and we choose g in the form 1 by x power n where n is less than 1. This is the strategy we follow for the finite interval. For the infinite interval, we check for the limit condition, limit extends to infinity f of x by g of x, and we choose g as 1 by x power n such that where n is greater than 1 for the existence of convergence. So please take a note of it. Then you will get the idea. After noting, please inform. Right? So if you consider limit extends to infinity f of x by g of x, it is nothing but limit extends to infinity, terms gets cancelled, 1 by 1 plus 1 by x whole power 5, and this is nothing but 1. Therefore, which is non-zero and finite value, therefore by limit comparison test, both the integrals converge or diverge together. So what are the integrals I am taking? Integral 1 to infinity f of x dx, integral 1 to infinity g of x dx, both converge or diverge together. Since the integral 1 to infinity 1 by x square dx is convergent. Why it is convergent? The power is greater than 1. Since it is convergent, the given integral is also convergent. That was the solution. Okay? Right. Let me take one more problem, then you'll have the idea. I think I just want to take 1 or 2 problems on it, then we'll get a concept. Suppose you have taken integral 1 to infinity dx by 2 plus x into root x, say. So, what is the function I have taken? F of x is equal to 1 by 2 plus x into root x. So, if you common x here, so 1 by x power 3 by 2 into 1 plus 2 by x will come. So, after taking common, whatever the part remained here, you take it as g. So, you take g of x is equal to 1 by x power 3 by 2. So, limit extends to infinity, f of x by g of x we consider. This is equal to limit extends to infinity 1 by 1 plus 2 by x. This is equal to 1, which is non-zero and finite. Therefore, by limit comparison test, both the integrals converge or diverge together. Since this integral is convergent, given integral is also convergent. Okay? So let me take the problem. I think this problem is also given the previous year papers. So you take that integral 0 to infinity x into tan inverse x whole divided by 1 plus x power 4 whole power 1 by 3 dx. Please take a note of it. Then I will go with the procedure. After noting, you please tell. Right. Now, please understand, while using the comparison integrals, we are always taking the part integral a to infinity. We are not taking integral 0 to infinity. So always the first part must be positive. It should not be equal to 0. So here what happens? The given integral will be considered as integral 0 to a x into tan inverse x by 1 plus x power 4 whole power 1 by 3 into dx plus integral a to infinity x into tan inverse x by 1 plus x power 4 whole power 1 by 3 dx, where a is greater than 0. Okay. So whenever 0 to infinity is given, we always split that from 0 to a and a to infinity. Sometimes you can split like 0 to 1 plus 1 to infinity, depending upon the interval and function constraints. That is up to you. But generally we always split, because for the infinite interval, the comparison integral is existed for positive number to infinity, not from 0 to infinity. Okay. So we are going to say that the given integral is convergent if the two integrals are convergent. So if you observe that this is a proper integral, because the interval is finite and the function is bounded. You cannot get undefined value within the interval. Accepted? Please check for the function. From 0 to a, if you take any positive number, x into tan inverse x divided by 1 plus x power 4 whole power 1 by 3 always will exist. Yes or no? Any questions on this? The first integral is a proper integral. How I am saying that it is a proper integral? Because the interval is finite and the function value is bounded. You cannot get undefined value for the function. Yes or no? So the first integral is a proper integral. Hence it is convergent. Now the second one is improper integral, because integral is not finite. It is a to infinity. For this we have to go for the verification by taking a suitable comparison integral. So if you take x power 4 common here for this part, so integral a to infinity, so let me say x into tan inverse x by x power 4 by 3 into 1 plus 1 by x power 4 whole power 1 by 3. If you take this function, again x comes to down, 4 by 3 minus 1, so 1 by 3. So this is equal to tan inverse x by x power 1 by 3 into 1 plus 1 by x power 4 whole power 1 by 3. So after doing the simplification, this part is remained. So you take this as g. So you take g of x is equal to 1 by x power 1 by 3. So if you consider the limit extends to infinity, f of x by g of x. So limit extends to infinity, the value is tan inverse x by 1 plus 1 by x power 4 whole power 1 by 3. And if you apply the limit, it will be pi by 2. Accepted? Right. So both the integrals, integral a to infinity f of x, integral a to infinity g of x, both converge or diverge together by the comparison test, the limit comparison test. And what about this one? Is it convergent or divergent? The power is 1 by 3 here. Divergent. Since the integral g sorry, is divergent, this is also divergent. So the first one is proper integral, it is convergent. Second one is improper, which is divergent. So the final result is given integral is divergent. Okay, right? I want to take the other problems. I just want to take one more interesting problem which gives the idea. Shall I proceed? So you take the problem that integral e to infinity dx by x into log x whole power n plus 1. This problem you consider. Now, how to do this? Very simple. So let us take that. You take log x equal to t. Then what happens? 1 by x dx equal to dt. So here from this you can say x is equal to e power t. So since x is varying from e to infinity, if x is e, then t is equal to 1. If x is infinity, then t is also infinity. Accepted? I am converting the given integral into another integral. Do you agree for that? So the given integral can be written as integral 1 to infinity dt by t power n plus 1. So it is just like of the form integral a to infinity 1 by x power n dx. It is of the same model. Now what we can say? If the power is greater than 1, it is convergent. So if n plus 1 is greater than 1, it is always convergent. So this implies n is greater than 0. So you can take any positive value for n here, then the given integral will be convergent. That was the conclusion. So here we are not taking any g of x. By simply rewriting the given integral into other form, we are stating that this is the possibility for n, so that the integral becomes convergent. Okay? Did you get the logic? Fine. Since the time is running out, we just have to finish one thing. That is, so far we have discussed about the convergence of the integrals having only one function. The final case of improper integrals is whenever you have an integral sign, say it is infinite integral or the finite integral, if we have two functions, then how to check for the convergence of the integral? It is just like first mean value theorem of Riemann integrability. So however, whenever you have two functions for the infinite integral, I don't want to write the limits here. So we are going to make use of two conditions. One is Abel's test, another one is Dirichlet test. So whenever the integrand contains two functions, by using one of these two tests, we will check whether the improper integral is convergent or divergent. And for majority of the cases, we use Dirichlet test. For some problems, we use Abel's test. So at the most, if you have taken 5 or 6 problems, you have done with this concept. Hence, we can conclude our total discussion of improper integrals. So I want to take these concepts on Friday, because I think tomorrow our class gets cancelled. We have other situation. So I want to take the thing on Friday, so that I will discuss about these two things, and we conclude the discussion on improper integrals. and one concept is left, that is uniform convergence. So if possible, 2 sessions are enough for this concept. So on Friday and Saturday, I want to discuss about these 2 things, the concept of uniform convergence. Hence, the whole part of real analysis will get completed, right? You can start doing the previous year question papers. And after the completion of this class, maybe today or tomorrow morning, I will give some problems postage, so which gives the idea over this improper integrals. So you can have a practice on this, because solving more number of problems is not at all useful. It's up to you to solve the problems, right? So I will give the whole idea and concept so that you can make use of these problems. Okay, so there is one small concept left for us under improper integrals. Then I will take 2 sessions on uniform convergence. Total real analysis will get completed. Then we start with linear algebra, the upcoming topic. So if all go well, I want to take the concept of linear algebra on Monday onwards. Fine. This is the upcoming module. Now you can give your feedback if you have any. If anybody wants to say something, you can share. So any other queries to anybody? Right? Then we will meet in the next session. Thanks to all.